Good afternoon. So this is the second lecture I'm giving. So first one was on data flow, and this one and the last one are on this language or system called Bluespec. And I will often use the word Bluespec and BSV interchangeably in these lectures. BSV is a very specific language, while Bluespec is a general idea, and BSV is a manifestation or an instance of Bluespec class of languages. So I debated a lot how I should present this work, because this is a language about hardware design. And first I was thinking this is a school on programming languages, so I should just give you the kernel of the language, describe it, and give you its semantics. But I think if I do that, you just won't get it, why we are doing it. It'll just become an exercise in symbol manipulation. So I will do that last. I'll do that actually in the next lecture. In this lecture, what I want to show you is what we need in a design for hardware language. How is it different from a design for software languages, and take it from there. Okay, so what is needed to bring hardware design to 21st century? So first of all, this statement implies that the hardware design is very, very retro from the point of view of programming languages. If I was to give you a sort of a strange kind of analogy, hardware design languages are at the level at which Fortran was in terms of programming, right? So Verilog has been invented, Fortran has been invented, which is used widely, and it does provide extreme convenience as compared to a wiring diagram that you may write by hand. And yet, there's a lot more that can be done. And surprisingly, it hasn't succeeded. I mean, so Verilog came into existence in early 90s or mid 90s. And its semantics are very ugly and defective, even today, after various attempts at cleanup. So when verification becomes the dominant reason or dominant cost in hardware design, then Verilog is really wanting. So you can view bringing it in 21st century means this language for hardware design must be informed by modern programming ideas, right, which you are very, very familiar with. So how will we apply it to hardware design? What does it mean? And the second thing is it must solve some special needs of hardware design. Okay, so if you see what is the problem in hardware design today, is there is very little IP reuse. If I publish something, if I publish a design, the chances that somebody else can use it without me being there to hold their hands is almost non-existent, right? So unlike libraries, etc., hardware, reuse of somebody else's design is very, very difficult. So IP refers to, in hardware terminology, intellectual property, right? So people design these blocks. You can say, oh, I have bought a block for 802.11 implementation, right? So that will be an 802.11 block that you buy. So that's why they're called intellectual property blocks, because often it requires a lot of domain-specific knowledge. The second thing is, unlike software, once you have written a package, a function, or something, you don't think in terms of, oh, if you use it like this, then I should tune it this way. If you use it like that, I should tune it that way. In hardware, that is the norm, right? If you have the same functionality, it will be implemented completely differently depending upon the requirements of the design. So much so that it's irrelevant that you could have used this design in that place, because people will say, but it's so much more expensive. It consumes so much more power, right? So the design concerns are such that reuse means that you must be able to get away with minimum power needed to deliver the functionality, deliver the performance you want for that block. And therefore, for the same activity, for the same functionality, there can be gazillion blocks in your library. The question is, can you still think of them as one block? Can you think of it as FFT, even though there are 15 FFTs in your libraries, and plug them and use them and so on? The other problem is the way hardware blocks are defined. It's very hard to use them in a black box manner. Sooner or later, you need what happened inside. So you can't just take this black box view of designs, and the moment you do that, then the problem gets infinitely harder. Because I'm not the one who designed it, and that's one reason why there is so little IP reuse, because people say, well, I'm having so much difficulty, I might as well design my own. Because that way at least I know, what is inside it. So these are some of the main issues. The other issue in hardware design is what is called ability to refine modularly. Suppose I have let's take a very common system. I have a processor memory system, right? I have a multi-core. I may have several processors and a memory system. It's conceivable that I have different kinds of processors connected to it. I may have, as it's called, wimpy processors, which may be just no pipelining or in-order processors, which consume less power, have less oomph in them, they don't compute as fast. And I may have very fancy processor, right, which is out of order, which consumes a lot of power, but also goes very fast. And I want to connect them to the same memory system, right? So you need some way of saying that I can take some module, refine it, plug in another one, without breaking the whole design. And we want pretty ironclad guarantees on this modular refinement. The other reason is that often these blocks are designed by different people, and we don't know how well they'll work in conjunction. So when we do performance analysis, when we do power analysis, only then we start learning, oh, this is the problem one. Maybe you should go and do something. You are the one who's consuming 85% of the power. Right? So let's focus on that block to reduce its power consumption and so on. So how to do this modular refinement without understanding the whole design, without having to worry about that just by changing this, I may destroy the correctness of the whole design, is a very, very major concern in hardware design. And then lastly, but not the least, whole system simulation has become very important. We live in an era, if you go back to 1980 when PC first came about, one of the great inventions was that somebody defined a platform. And after that, Intel could go and do its own innovations on the processor side, right? And software, buffeted by Microsoft, could do its own innovation. There was some interface, which we call ISA, and it's more than that, when you bring operating systems, etc. So those things. Now we do so much design where hardware and software interact so closely that we need to simulate both together. If I want to understand the performance of some complex algorithms where I'm using hardware accelerators, it's not good enough to simulate the hardware independent of software, right? Because they're really co-designed and you can move things back and forth at the design level. So all these three things are quite important if we want to do hardware design in such a way so that it reduces the cost of hardware design, because hardware design is quite expensive. Let me tell you a story. So I had this fabulous semiconductor company, so we were building 10 gigabit chipset, and it had about 50 engineers, hardware engineers. And one day I found out, purely by chance, I was talking to some people, that this design had 26 FIFOs in it. Okay. All right, what's the big deal? 26 FIFOs. The next statement was shocking to me. They had 23 different designs for FIFOs. So that tells you, and I'm talking about FIFO, literally nothing else, FIFO. A simple block like that has 23 different design instances. in this design. So I was really mystified by this. I said, why don't you use his design? It doesn't quite do what I want. I said, is it a FIFO? Yeah, it's a FIFO. It doesn't do what I want. So it made me so curious that I was actually going on a trip. So I downloaded the description of hardware FIFO from internet, right? So first shock to me was, it was 23 pages long. Right? This is not about how that FIFO is implemented. This is about how to use that FIFO. I'm saying, wow, this is really cool, right? That to understand how I have to use this FIFO, there is 23 pages of description associated with it. So there is this picture. And then when you start reading it, you will find statements like this. An error occurs if a push is attempted while the FIFO is full. Yeah, sure, makes sense, right? Okay, what does this say? Thus, if there is no conflict in simultaneous push and pop when FIFO is full, a simultaneous push and pop cannot occur when the FIFO is empty. And it goes on and on. It'll get more bizarre. Read the next one. The pop operation occurs when pop request n is asserted low, as long as the FIFO is empty. Asserting pop request n causes the internal read pointer to be incremented on the next rising edge of the clock. So this 23-page description not only has all this kind of description scattered all over, but there are timing diagrams which is saying, don't do this on this clock cycle, otherwise everything will go wrong, etc. No wonder that there were 23 designs in my company, right? Why would you put up with this, right? He says, he doesn't know what he's doing. My FIFO is better for what I'm doing, okay? So, and furthermore, there is no systematic way of reading this document because these constraints are spread all over the place, right, in this document. So somebody says, should I do this or not? He says, yeah, look at page 13. Whoa, so not only you have to read this 23 pages, but you have to kind of internalize it a little bit, what is allowed and what is not allowed. The main point I want to make is no machine verification of such informal constraints is feasible. So if I'm going to use this FIFO in my design, what choice do I have except to go and look inside the design and then somehow code all these constraints that I have outlined in red, because they're not going to be enforced by Verilog. They will just cause errors, so you have to understand you should not do these things. Okay, so what I want to show you is how can we approach this problem informed by modern ideas in programming languages so that this problem doesn't occur, and Bluespec is an attempt to solve that problem. So let me just say from the onset, Bluespec is a new way of expressing behavior using guarded atomic action. This is still controversial. This was a radical idea when we proposed it, around 1998 or 1999. People say, oh, these academics, right? Guarded atomic action, what is that? And now you say that you can design hardware. But let me just present you what it is. So a module, like an object in object-oriented language, has a well-defined interface. So when you think of an object-oriented language, what is the interface of an object? What can you do to the object? Sorry? Well, I think you can essentially apply methods of the object, right? So methods define the type or what is legitimate to do to that object. This is how we think about it as software people. There is no reason why we should not think of the interface of a hardware box the same way. That these are the methods I can perform on it and nothing else, right? If you start pressing wires and buttons willy-nilly, then you should not be surprised if fire comes out of your box. So I think this is the first idea. The second idea is, now this is where you're going away from software language. The idea is a method may not be applicable when you want to apply it. So you think of these objects not something dynamically allocated, but something very concrete. So you have n of these objects which you're going to be manipulating. And then an object, you say, please do foo. The object says, sorry, I'm busy right now. Because it may already be computing, right? The old computation may not be done. And remember, we don't want to look inside the object. So we have a guard coming out which says, this method is not applicable right now. So that's the second idea, that methods are guarded. A method can be used only if it's ready. And the third thing is, now I have various modules. How do I connect them together? And that's where guarded atomic actions come into picture. You will specify some action. You do this, you do this, you do this. By that I mean call these methods from different modules. And atomic action says either all of them will be applied, either all of them will be successful, or none of them will be successful. Right? So this is giving you a way of coordinating things across modules. By the way, these slides are on the web, so you can access them right now. Okay. So one way I'm saying is, so you have understood something about module, which is like an object in an object-oriented language. Some restrictions on its interfaces, they have to be ready. A method has to be ready before it can be used. And think of how these boxes are connected, the glue, in terms of atomic actions. That you must do this, you must do that, and you must do that. Either all of them succeed or none of them succeed. Nowhere I'm going to talk about a structural wiring diagram between these things. But ultimately, that is what is going to result from this high-level language. That's what the compiler will do. Okay. The atomic action can execute only if all the called methods can be executed simultaneously. All right. Enough of abstraction. Let's look at a concrete example. All right. And we'll start, as we often do, for pedagogic purposes, with this very, very simple example, greatest common divisor, and we'll implement it using Euclid style stuff. So you're going to make a lot of money by implementing GCD in hardware. So let's get on with it. All right. So, and this is not one use kind of a thing. So I want to build this box, GCD box, and I want to continuously feed it inputs and take away outputs, from it. So that's the high level picture I have in mind of what I want to do. And, roughly speaking, this is what not roughly speaking, accurately, but I will explain more details as we go along. The interface of this GCD is what? You're defining two methods on it. One is called start, and the other one is called get result. And I call them action kind of methods because they affect the state of the box. Right? You could have had read-only methods, which only sense something that is going inside the box. But these are actually going to affect the state. So what do you think the first one is trying to do? Start. What is it telling you? It has two inputs. And these inputs are of size 32. Anytime you see this, number sign, it's a parameter. So you could have written whatever you want there, including n there. Okay? So, and get result, what does it return? A 32-bit quantity. A good beginning. I mean, GCD, if I start with two 32-bit numbers, I get a 32-bit number back. Wonderful. Now, what is this invoke GCD stuff? Right? So I'm taking things from input Q and putting them into. So basically, what I want to do is I want to start the GCD, give it X and Y, right? But X and Y, so I'm assuming this is coming as a data structure which contains two things. So this is the first element of the tuple. This is the second element of the tuple. So you're extracting from the first element of the queue. Input Q first, First element is X, second element is Y. You have to do one more thing, right, in order to start it. Then you say, I'm done with this. After that, input Q will be dequeued. This input will be taken away. Now, do you understand the value of atomicity just by looking at this rule? It will be a disaster if you started it and didn't dequeue, or vice versa. You dequeued it but forgot to start. Neither of those things are acceptable. So either both acts should happen or neither should happen. Okay? Yep. It's an atomic action. You're specifying. Remember, so rules are going to be like the glue for connecting things together, and that's what I'm trying to show, that these are the modules which have some state in them, and now I'm giving you some way of connecting these things together, and these are atomic rules. Okay, so atomic rules will always be just ultimately pure combinational logic. All right, and get result, what does it do? So this is action method, action value method. So it returns something, GCD get result. It returns X over here, and you enqueue it in the output queue. Again, you can see the importance of atomicity here. Once you take it out, you must put it somewhere. Otherwise, it will get lost. Yep. Sorry, in what process? No, we are not programming anything. We are trying to build hardware to implement GCD. So this hardware box, the hardware system I'm building, keeps sending requests to this GCD box and keeps taking requests out from the GCD box. So this is just a driver, if you want, put things in, take things out in a systematic manner, from it. So obviously we design very, very complex hardware, and that's not what this talk is about. So if I was to design that, I will decompose it. I'll show you what are the modules, how they're connected, what are the rules for moving data around in them, right? But let's just understand the basic concepts here. Okay, so the plan for the rest of the lecture is, I want to explain using GCD, this concrete example. What do I mean by guarded interfaces, guarded atomic actions? Most importantly, hardware generation, because my goal is not to execute GCD. My goal is to build hardware, give you a register transfer description of GCD at the hardware level. That's what the compiler will do. And then, let's build also a high-performance GCD while we are at it. Okay. So now, I hope I'm not being presumptuous. What background does this class have in hardware? How many of you have taken introductory logic design course when you were undergraduates? Fantastic. So then I'll go over it very, very fast in this tutorial. Okay, so finite state machines, so this is just terminology. So I use the word sequential machines all the time because I'm a double E, so sequential machines, sequential circuits. So FSM is a mathematical object, so you are all familiar with Boolean algebra. You probably have seen gazillion different representation of FSMs, either as circles connected with arcs, Mealy machines, Moore machines, you name it, right? And you probably also know all kinds of mathematical properties, how you can show the equivalence of them and deterministic versus non-deterministic. Those are all mathematical things, right? Properties, which we'll never violate. We make full use of them, right? So when I say sequential circuits, to be exact, what I mean is synchronous sequential circuits is a method to implement FSMs in hardware, and usually it's drawn like this. So the way to read this is you have some state elements, some storage here, right? Which can only be updated on this clock, right? So clock is very regular, right? It just comes. So when you say, I want to run my GCD at 2 gigahertz, that's the clock we're talking about, right? How fast you want to run this thing. And that depends on many, many things, totally beyond the concept of topic of this lecture today, right? But the point is then we define combinational logic, which determines both the next state for this thing as well as what is to be produced. So you can put inputs and you can take outputs. So this is our general notion of a synchronous sequential circuit, that there is a clock at which the state changes of the machine. Okay, now first clarification, which you never find in textbooks, is yes, it's true, your computer may be a synchronous sequential machine. You never think of it like that, right? You only think of hardware in terms of cooperating sequential machines. There are lots of them, lots and lots of them, right? So essentially what we need is two things. We need how to design these sequential machines, and then we need very powerful techniques for composing them, right? As long as we have that, then we have that computer science kind of a closure, because once you have composed, then we'll get another sequential machine, right? And we can compose it further. So you're very used to this in terms of both functions and objects, and I'm going to borrow these ideas from software completely, 100%. Okay, so the next thing is, what is this storage element? So again, we simplify our lives and we have only one storage element, one type of storage element, and it's called D flip-flop. In fact, D flip-flop with an enable, so that red sign is an enable. It stores 1 bit of information. And what is its functionality? So suppose enable is 0, right? We don't care what the data is. We don't care what is on this input. Whatever was stored inside this is what will show up in the next cycle over there, right? So if enable is 0, the value holds. Whatever is in there will hold. And if the value is 1, then we don't care what is stored inside. Whatever we are supplying is what will show up a cycle later, right? So you'll copy inputs. So does everybody understand the functionality? That unless the enable is on, you cannot change the state of this thing. Yep. So we want control over when storage will be updated. And we don't want to rely on clocks, because clock is going on and on and on, right? So it's a detail for us that these changes only happen at a clock cycle. For us, what is important is no change can take place unless I give you an enable signal. And another reason is then after that you never have to worry about clocks, because look at this description. I did write QT and QT plus 1, and there is a very good reason for that, right? But it's a conceptual thing at this point. You don't worry about clock inputs. I won't even show it. Just to give you a little bit more insight, because remember, this is the tutorial on hardware, in this. So one way to think about this is that, whatever value you have, you keep circulating, right? But if the enable is 1, then what do? You take the new input. That's one thing you have to understand. The second thing you have to understand, and believe me, this is the only slide with a timing diagram, right? So, okay, this clock, right? Going idealized clock, absolute perfectly square wave, right? And you have enable signal that came and it went high here. So that means no change can happen here, regardless of what you do to data, right? change can happen here because enable is high. Okay, so now if you look at Q was low, so it remains low even though data will go high because D is high and enable is high. And then notice again, the interesting thing about this is enable went down here. So even though data went down, the Q didn't change. Because the only way change can happen is enable has to be true. If enable is not true, then it remains the same. Now, if you were studying real electrical engineering and circuit design, then we'll tell you what nasty things will happen if these things happen too close to the clock, right? Metastability and all these wonderful ideas you will have to learn. As far as we are concerned, when you see that level of problem, you should immediately get up and say, not my problem, somebody else created it, right? Low-level tools, different levels of tools. High-level designers never worry about such things, right? Because if they started worrying about this, you won't get off ground in complex hardware design. Okay. So because of this, data is captured only on enable when EN is on. This kind of circuit is often called edge-triggered flip-flop. Changes only happen on the edge when the enable is high. Enough of this. Let's get on with our design. So now what is a register? A register is nothing but bunch of D flip-flops. All of them are controlled by the same enable. Right? So I don't have to think about them as individual flip-flops anymore. I can say, was this register updated or not? Just give me the right enable value, right? If enable is true, then the register can change. If enable is false, register cannot change. Yep. Sorry? Same registers that you have. Yeah. So that's the language issue, right? So if you declare it n bits, hardware will be instantiated for n flip-flops. Yeah. And you can also have a register file, right? You have 1 bit for 1 flip-flop, right? One flip-flop represents 1 bit. A group of registers with a shared set of input and output ports. So what happens is that sometimes when you have lots of registers, you may not want to control them independently because that takes a lot of hardware. So you will say, well, I have 32 registers. I'm only going to be reading 2 of them. So I'll say I have a port, right? 2 ports, read ports. I only update 1, so I have 1 write port, etc. Okay, so just a summary of what's a clock sequential circuit. Any sequential circuit can be built using D flip-flops, right? The state of the flip-flop can change only when the enable is on. The change of the state can only be seen a clock later. This is something you have to internalize because this is different from software. So what's going to happen here is I have a register, somebody's reading it, right? And somebody's trying to update it. So the readers will see the current value of the flip-flop, not the incoming value. Incoming value can only be seen a cycle later. Okay, in a circuit with single clock domain, all flips are connected to the same clock. And therefore, clock inputs are not needed in BSV description unless we design multi-clock domain circuits, where there are multiple clocks. And of course, there are many circuits like that, but that's an advanced topic. Okay, so for today's lecture, for the semantics we'll present tomorrow, it's all single clock stuff. Okay. Now, a module in BSV describes a sequential circuit. So this is what you have to internalize now. Every time I use the word module, what's going to be produced? A sequential circuit. Compiler will help us produce that sequential circuit, but a sequential circuit will be produced. It has internal state. It has internal state can only be read and manipulated by interface methods. and an action method specifies which state elements are to be modified. And again, it's all or nothing. If you say these state elements should be modified, then all those will be modified, or none of them will be modified, which is precisely what we want in a sequential circuit. Remember, I showed all the state like this, and you have to update only those things that you want to, right? All right, back to GCD. Are you ready to design GCD now? So first you have to choose algorithm for doing GCD. So I'm going to use the classic Euclid's algorithm because it doesn't involve multiplication. So let's refresh it. So I'm trying to find the GCD of 15 and 6. Does anybody remember the algorithm? Right? Subtract, so you get 9 and 6. Subtract again, you get 3 and 6. Oops, the first argument became smaller, so you do swap, right? 6 and 3, and now you subtract again, 0 and 3, now you found the answer. 3 is the greatest common divisor of all those things. This is the Python program for doing this. Please remember, our goal is not to imitate. This is not yet another, I'm not presenting you yet another way of writing GCD. The GCD we are writing, its goal is to generate a circuit that does GCD. Okay, so very first thing you do is you declare all the register elements. What is the state of the sequential circuit? What is the module GCD? So, by the way, by writing it like this, I'm saying I want to make a GCD, and the interface of this is specified by GCD, which I had given you earlier, the interface definition. All right, and now can you read what is this line saying? Make me a register which is 32 bits, we'll call it X. Make me another register which we'll call Y. And what is this 0? Initial value is 0. In this, and because my GCD I'm not going to compute instantaneously, so I'll have a busy flag, which I start out by saying I'm not busy. Okay, so now you told me that it has an interface. An interface specified these two methods. Remember that? Okay, so who can write down the definition of start? What will start do?
Check A or each operator and
You are computing. I'm just trying to start the box.
copy to X and Y.
Exactly, right? So you say X gets A, Y gets B, and busy flag is, now I'm busy, right? And when do you want to do this? Can you do this anytime? Right? You have to worry about the fact it's not busy, so therefore there has to be a guard here, which says if busy flag is false. Are you with me? This method makes sense, right? Okay, who's going to tell me the next one? Get result. Well, we know when we get the result, we're going to mark the busy flag false, and we're going to return Y because the result is going to be in Y. But when is the result ready? When? No, more. When X is 0, right? Okay, so and I have to put this also here because, who knows, you had initialized X to 0, right? So it has to be busy before you say I computed something which you can have. Okay, so good news is we got started and we can pick up the results. Now only detail left is how to compute the GCD. Yes? Yeah, I mean return just is like a syntactic thing. It's saying connect these wires. These are the wires that are going out.
Sure, but specifically that nothing wire those.
So this is simply the output of this Y register. Remember, there's a register Y, and its output wires, its wires are connected. That's what is being returned. So there is no computation going on.
Just asking the argument.
Sorry, which argument?
The 32 bits that are being passed in.
So in the get result, here there are arguments being passed in. This is the return value. So it's saying Y must be 32 bits, right? And compiler will do enough checking to tell you, oops, you blew it, on the types or something. Okay, so now actually write down the rule for computing the GCD, and this is what you were saying, right? If X is greater than Y, then X gets X minus Y, right? That was the subtract rule. And if X is not equal to 0, then you say swap it. So what can you say about this rule? Just think, we are always trying to apply all the rules we have got. So what will happen to this rule? When can you apply it? It doesn't do much GCD executed repeatedly until X becomes 0. And after that, it's just no state change. It will remain in whatever values it has at that point. No. A and B were input wires, right? And Y is the output wire that is going out. So this is inside the GCD, and what you saw earlier was the outside view of GCD. Okay, so now let's examine this rule again, right, which I showed you here. And what it says is several things. A rule is a collection of actions which invoke methods. So in this trivial case, all the methods I'm invoking are just doing some reads and writes on the register, or some very simple arithmetic, X minus Y, or some very simple comparisons. You should be able to visualize any of these things are trivial in terms of combinational circuits, right? I can design a circuit which will know how to generate a true or false depending upon whether X is greater than or equal to Y or not. All actions in a rule execute in parallel. So there is no sequential reading in this. Right? So in this case, look at this one. X gets Y and Y gets X. What is the effect of that? They're getting swapped, because whenever we read the existing values. And whatever we are writing is not going to be visible until the rule execution is over. It's only visible in the next cycle. So these things stand for register assignments. So whenever you do that, that's when enable will be set implicitly, right, for the register. A rule can execute any time, and when it executes, all its actions must execute. Atomicity, atomicity, atomicity. Okay. So now I want to sing praises of guarded interfaces, right? So essentially, I could have defined a language for you, and semantically, actually, they are not needed. Guards are not needed, right? I could have defined a language for you without guards. But there's such an enormous user convenience, right, that you don't want to do without guards. And I'll illustrate that even in this simple setting. Okay, so convenience is this: includes some checks in the method definition itself to avoid having to test the applicability of the method from outside. You see, if I did not check from outside whether method is applicable or not, then I'll have to have another method which will tell me, oh, I'm busy, right? And the protocol will be, please don't invoke this module until the busy says it's not busy, right? So if you're going to do it every time, we might as well make it part of the method. Okay, so this is very, very important when you think of the FIFO abstraction. So my FIFO abstraction has 3 methods in this: NQ, DQ, and first. First returns n bits, right? DQ, you just DQ it, and NQ, when it's ready, you can NQ it, and you have to give me n bits number, n bit value, which has to be stored in it. Now here is the main thing in the language. Every method is guarded. Every method has, so if you have a method, there is always this green line which says, I'm ready or not ready. You don't know what it means from outside, right? All you know is this method is applicable or this method is not applicable. So you are abstracting away the details of why it is busy, right? You're just saying it's busy. Okay, so the semantics at some high level would be, but for all you know, your implementation may be lousy. It's really not full, but it's, I don't want to look at it, right? Or something, in hardware terms it's called, it may have a dead cycle in it, for whatever reason it couldn't get on with it. So the value returned by a method is meaningful only if its guard is true. So for example, if the ready is not true, this is always going to be giving me some value. But to find out whether this value is valid or not, you always have to look at the ready wire. Every action method has an enable signal. So you have this enable, which says, do it. So think of it as a box with lights on it. So green light tells you what? It's ready to go, right? And red light is the button you press. You say, please NQ, but before you press it, you might as well supply some inputs, right? So all those n bits better be there before you press the red button. So if you go back to, not go back, this is the interface of the FIFO for you. And please notice, in the interface definition, there is no notion of enabled and ready wires. They're all implicit. How do I know that I need an enable signal? Types tell me, right? Action, action. No action here, right? I don't need an enable. I don't have to worry about ready because every method has a ready signal coming out. So that's just universal. Everywhere you have it. Okay, so does this make sense? Guarded interface? Now let's understand the implications of it. Oh yeah, by the way, rules can also have guards in them. So you have rule foo here. If P, then X. So how do you read this? This rule should be executed only if P is true. Otherwise, no op, right? Nothing should be done. This is called explicit guard of this method. A rule can execute only if all of its explicit and implicit guards are true. Yep.
You say this is a edge trigger semantic, so that if really one of the P's are ones, if you transition from 0 to 1, execute.
No. You should think of any signal in this system as if you're reading some register. Right? So P either is directly coming from a register or you're applying some combinational function to a register. It's a level kind of a signal.
When you're reasoning this language, you're probably thinking the normal way we think the software.
Right. Variable value is this, right?
Semantic of the things that happen, edge, trigger, etc., is consistent with this. So we don't need to worry.
Exactly. You never have to worry about edge triggered or anything, right? So next time, in the next lecture, when I give you the semantics, at that point you have to know nothing about hardware. Yeah. So I have faced. You're asking a very good question, and that has been the, battle I have been fighting for the last 15 years. That you can program at such a high level, and I'm not even willing to concede a single gate. I mean it seriously. I mean, I'm saying I'll take you on. If you want to do a wiring diagram and show me a better circuit, show me. Right. No, abstraction is designed not to introduce any overhead. Right? So whatever we do, end up doing in hardware, was going to happen in your circuit too. It's just a different view of it. Right? So I'm looking at it in a much more systematic way. So there is going to be no sacrifice in terms of efficiency of hardware generated. Okay, so back to this example. Right? You have seen this rule before, and you have seen this rule before. So please tell me, what are the explicit guards? What is the explicit guard of this rule? True, right? There is no guard in this. Same thing is true here, right? What are the implicit guards? Let's talk about this one. What are the implicit guards? That start better be ready, right? And input Q better not be empty, right? So you can now imagine how the guard for the rule is constructed. You're going to take all these implicit guards, conjoin them together. And that's how you will produce the guard. What about there? What is the explicit guard is again true. Implicit guard is get result better be ready, and Q better not be full. Q better be ready for an NQ. Okay, this is a value action method, which that's why that left arrow shows up over there. Now I want to point out some other properties of this interface, which is equally important for the kind of circuits I want to build. So this module that we have defined for GCD is what I call latency-insensitive interface. You give me some inputs, sometime you will get an output from it. Whether you get it 1 cycle later or 10 cycles later, you have no idea. You have no control over it. Because for that, you will have to go and look inside the module, right? You can't look inside the module because all the compositions have to work based on the interface. An interface says nothing about what is the relationship between input and output. Certainly not any timing relationship. Okay. The interface also does not tell us if GCD is pipelined or not. Okay, so what would happen if it is not pipelined? Once you start it, it becomes busy, right? And until when it remains busy? Until somebody picks up the result, right? Completely disconnected event, right? But we know from our implementation was not pipelined. But I can change the implementation, I can make it pipeline or do something, right? Nothing will change in the use of it from outside. Okay, the interface also does not tell us if the results come out in order, because all I'm showing you how to start it, and I'm saying pick the results. In the interface, there is no assertion about what is the correspondence between input and output. That's in your mind. That's in the designer's head. So if you designed a very fancy GCD where the results may not come out in order, then how will you know which answer you're getting? You'll have to do some tagging. You will have to say, oh, this input has tag T on it, right? And the answer I got had tag T primes. Ah, okay, I have to wait. You may want to, the tagging has to be such, but that's beyond the language level. That's a higher level idea here. Easily implementable, but it's higher, it's outside. Language is not supporting it. Yep. No, because that data dependent.
How do we know that how many cycles add operation takes or multiply, and when we find these cycles in the complete program, we can calculate using hardware?
So at the composition level, you have no clue about these things, right? I mean, it will take whatever cycles it takes. The only thing you know is if it's a combinational circuit, then effectively it's happening all simultaneously, right? Preserving the data dependencies. But if you look at the, under the hood, then you understand the propagation delay through the combinational circuit. But from our point of view, we have no clue here how long this GCD will take.
This is true for
Everything you will design in this. The whole concept of module is it's a latency-insensitive interface. It strongly discourages use of any modular packing where you want to rely on timing information, because that's one of the biggest sources of error in this.
when we write program higher level,
Mm-hmm.
we can always look at it and we know that these are the elementary operations
Yes.
in this program.
Mhm.
We know that add operation takes one cycle, multiply of
That you can do.
cycles.
Right.
How do we know that? You are saying we cannot look inside the module and we
No. So if you were doing performance analysis, then you will look at inside it. I mean, there'll be tools. I mean, in hardware, it's much harder than it'll be in software, because you'll have to see how that library is implemented. What is the exact RTL description? Actually, that's a very good question. Let's wait until we see something about hardware generation, I think, which is, in the next lecture, this lecture, I don't remember. We'll see. Okay. So here is my high performance GCD. Can anybody guess what I'm going to do? I'm going to instantiate the GCD I showed you twice, right? And then, when things come in here, I send them here. Next one I send here, and similarly, so that's what is. With the same interface, but with twice the throughput. A variable turn I can be used to start to direct the input to the GCD. So you have turn I. You can initialize it to true, so then it sends it here. Next time it will send it here. So you keep flipping it, right? And you can similarly play the similar trick at output. Yep. No, it's not simulating. You are not thinking it properly. Our goal is to get very rich by building the world's fastest GCD, right? We are not interested in any other computation except GCD for the purposes of this lecture, right? So I'm just showing you better and better hardware for building GCD. So we already saw one. Somebody says, I have a better algorithm than Euclid's. Okay, so we could have tried to do that. It might not fit in one lecture, but right? So now what I'm showing you, even with that very simple algorithm, I can still build you hardware which has twice as much throughput. And the hardware, what we did in the previous GCD is going to go in here. And then I'm going to put some more fuzz outside, and this will again behave. It has exactly the same interface. Can you implement this one? All right. So this is my high throughput GCD. What is its interface? No, GCD, right? Interface is the GCD, the module you are building. And that interface says you need two methods, right? Okay, now let's see who's going to help me. What are the state elements in this? I instantiate. This is make multi-GCD, this is make GCD. This is the one we have already done, right? So you know how that one works. Oops, sorry. I've instantiated these two Boolean variables, right? Registers, initialized to false. And now what will happen on start?
You will see if the first one is busy or not.
Not busy, you'll read the value of turn.
And value of
Got it? Right? So if turn is this way, then you go and start GCD1, else you start GCD2, right? And then you flip the turn. Does it make sense? Yep.
At one time, one GC.
No. You will start the first one, right? And suppose immediately you saw another input come in. What will happen? Then this rule can fire again, right? And it will put it in the next one, right? So both the GCD are computing in parallel. And it wouldn't matter what order they finish in, the results will go out in order because turn will wait for the result from GCD1, then it will get the, so the results will go out in the same order in which we invoke them. You like this GCD program? Right? Do you agree that it has higher throughput? As is often the case, whenever there is higher throughput, there is more hardware. It's very easy to see this has at least twice as much hardware. You have two GCDs buried inside it, plus all the glue logic. State-wise, not too much more. I mean, the only extra state here is this, 2 bits of state. But the GCD itself has been duplicated. So whatever state was inside GCD is all being duplicated. So area-wise, this is going to be at least twice as big. Let me do one more example, very simple example. So as the diagram implies, what am I trying to do? I have some input queue from where values are coming, and I want to send the red tokens to the red queue and green tokens to the green queue. Okay, so does this program make sense? What is it saying? If it is red, then enqueue it in the red queue and dequeue. Otherwise, it must be a green token and enqueue in the green queue. Do you think you can write such a program? Yes, right? This is pretty trivial. Who's going to tell me what is the implicit guard here? This is much trickier than you think. Think. What is the implicit guard here? One thing we can all agree on. This thing must be non-empty, right? So depending upon if it is red, then you want to check if the red queue has space. On the other hand, if it is green, then you want to check, right? Because if it is red queue, you don't want to check the green queue. Sorry?
We don't know that until we read. We don't read until we know the other 3%.
You don't know anything. Compiler is going to do this for you. Compiler is the one that pulls out the implicit guards, and it will pull out the implicit guard. Would be this, right? So basically, the only thing I'm trying to show you here is this thing is absolutely algorithmic. I mean, everybody in this room is capable of deriving this, right? But it's tedious. And because of all this, you say, man, I love guards. Because you don't want to write all this stuff. You want to write it like that. Yes, this simple example gives you some reason to believe in guards. Almost sounds like gods, right? But I meant guards. Okay. I could have also written that program in this way, which is in some sense more appealing. So what I did is I turned this into a guard. I said, if this thing is red, then enqueue in the red queue. If it is green, then these two programs, from our point of view, are equivalent, right? It wouldn't matter which way you write it, so it's a question of taste. right? Which one you prefer to write, because only one of the rules can be active in a given state. These rules are so-called mutually exclusive rules. Man, I have no idea how many slides do I have. Okay, hardware synthesis, we are on. Okay, so you have some clue about how to express this hardware, right? We are not building a microprocessor yet, right? We are just designing GCD. So let's make sure we can generate hardware for GCD, right? So synchronous sequential machines look like this. And the way we are doing it in BSVs, we are declaring lots of registers. And registers have enables, that's what those red lines are. And registers, you have to supply some input and you can read the output. So this is roughly the picture for every register you will declare, and its width is completely dependent upon the type declaration you have given it. Whether it's 32 bits or 10 bits or 17 bits, up to you. All right, and they all have the same clock. We don't bother with it. It'll just complicate the diagram, right? And then there is going to be combinational logic. And what is the goal of this combinational logic? It's going to tell me the input for each register. It's going to tell me the enable input for each register, whether I should update it or not. Right? And it'll do it for each register. So that's the kind of circuit we want to generate, because the goal is to show that every module results in a sequential circuit. And of course, this may have input wires and output wires going in and out of it. So each register and its width is declared explicitly, so it's very easy to draw that top line I drew for you. Okay, all registers are driven by a common clock. You have no control over it. We won't draw it in this. Combinational logic is derived from the rules and methods you write, and that's what I want to show you now. And your program defines the input value and the enable for each register, every cycle. Okay, so, and each rule generates an enable signal for each register, it says directly or indirectly. So back to our, before GCD, let's do FIFO. We want to go easy on ourselves, so our FIFO has exactly one element. In hardware, you'll be amazed how far you can go with one element FIFOs. Right? But it's very important, an abstraction, to think of it as a one element FIFO. So how am I going to implement this one element FIFO? Right? So this is, you already know this is the interface, and I have a data register that will hold the register. Oh, by the way, I've never explained what was this T. Huh? No, it's more sophisticated than that. Type. Right. So whatever type you have, the compiler will bitify it and say, what is and then it'll allocate the right size. So we will draw a big distinction between registers that can hold integers versus registers that can hold something else, versus say, no, I'm just going to think in terms of bits. So then it'll be bits size you will define. Okay. And then I have another 1-bit register which tells me whether it contains anything. Right? It's empty or full. And which methods I have to write? NQ, DQ, and first. All right. Does this look good? When we have to NQ, then V gets false, but guard. What is the guard? Sorry? Yes? And first, there better be something before you read it, and it just returns D. NQ, D will get X and V will get true, right? And guard. How do you like my implementation of one element FIFO? Not bad, right? You did not know that to generate one register and hardly any logic can take so many lines of code. But believe me, we'll rely on the property of this FIFO and use it with impunity as as our designs get more and more complex. All right, so now I want to show you the exact circuit that will be generated for this FIFO. You're up to the task? All right. This much makes sense? We have a D value and we have a V valid input, right? And for everything we need input wires and we need enable signals. All right, and this is our interface. We have NQ, DQ, and first. Make sense? Who writes in D? Yes? Who writes in V? Ah, that's complicated. Okay, we'll come to that. Who sets D only NQ, right? So it will be enabled whenever NQ is enabled. And when is NQ ready? When V is false, right? Does this partial wiring diagram, does it make sense? Right? So when you NQ, you're going to connect it to register D. And depending on the value of V, whether you can do it at all or not. And its external protocol, compiler will have to worry about never to press NQ unless the ready says true. Okay. I'm doing the easy ones first. Okay. So first, do you agree that this is the data that is going out? And what is the ready signal? Good. So I reserve the most difficult one to the last. So as was pointed out, both NQ and DQ want to change V, right? Oh, there was one easy thing left. So DQ can be ready when its V is true. Okay. Okay, so now we come to the hard part. Right? We are looking at both the input, those signals coming in, and based on that we will decide. So what is in that question mark? What is that logic? Okay, let's draw it, right? So this is just to remind you, we have NQ enable signal coming in here, DQ enable signal coming here, right? And we have to produce the data part of V, and we have to produce the enable signal for V. So what is the value of V enable? If either of these is true, you want to write it, right? So it's OR of these two incoming signals. Boy, I really did it. The easy things first. Sorry, yeah. I think all will do. You can probably do exclusive or two. There'll be huge problems if both of them are true simultaneously, right? Fortunately, that cannot be the case here. Why? Because the ready signals are mutually exclusive in this FIFO, right? One is V, one is not V. So therefore, their ready signals can never be true at the same time. But if they were true simultaneously, hell will break loose, right? So that's the topic of next lecture. How do we deal with all those issues? Here is just a very simple example. So all I want to do is I want to put a true in here. If this is NQ is true, I want to put false if this is true. So I just did it like that. There may be much, much simpler signals than that. But if you roll up your sleeves, you'll be able to derive this circuit. But always remember, you don't have to derive anything. Compiler is doing it for you. So this is what goes in that question mark. Okay. This is the main picture I want to draw for you. So I have taken whatever I did on the previous slide and I have just redrawn it slightly. I have redrawn it in terms of what are the input wires and what are the output wires. Because that's how we think of our circuits, right? What I want to do is I want to think in terms of this. Every sequential circuit that we will have, everything we will have input wires and output wires. And ultimately, the compiler has to connect all these things together, right? And that's what we want to understand, how these connections are made. But do you believe me? Just think about it for a second. Are these the inputs to the FIFO module? Obviously, these are the inputs, right? Whether to NQ, whether to DQ. Obviously, you have to supply the data. What are the outputs? Data comes out, right? And it have to supply the ready signal for each method. A module is a sequential circuit with input and output wires corresponding to its interface methods. I could have drawn all these wires for you without looking at the implementation of FIFO. Because I know what are the input wires going in, what are the output wires coming out, just based on the interface. This is just to take you back into the present world. If you thought of this FIFO in terms of state transition diagrams or state transition table, believe me, your head will hurt, even though it's one element FIFO, right? Because the number of signals is so huge, right? For each thing, you have to specify what's happening now, what's happening the next time. And furthermore, the biggest headache is this. There are many inputs which are illegal, right? Because you say, no, this should not be true at the same time. And this transition table kind of diagrams are not very good at that. I mean, you'll be writing comments in the margin. Don't do this, bad, right? Well, what we want to do is we want to generate all this information automatically so that it can't be violated, because compiler will be dealing with it. Okay, constraints on the use of methods in a FIFO. BSV compiler makes sure that NQ is not set to true unless the NQ ready is true. Very important for us, because that's a very, very high level invariant in Bluespec that no enable can be set unless the corresponding ready is true. Okay. Your code is such that NQ ready and DQ ready cannot also be true simultaneously. Thus, the input for V register is always well defined. Right? More on this topic in the next lecture. I was wondering, where is this? Okay, thank God, next lecture. Okay, but I have a few more things here I want to do it quickly. Streaming of functions. So suppose you have a combinational circuit F, but I'm just sending volleys and volleys of input to it, which will come out, right? So you have this, I'm showing you the input Q side and the output Q side. I just want you to get comfortable with the circuits that are drawn. So what circuit will be generated for this? The output from input Q is going to be transformed by F and stored in or sent to, right? So we have this, suppose we know how to build this combinational function, then we are connecting this and we are connecting. You're with me? Wonderful, right? When can this happen? This has to be ready, right? And DQ has to be ready. Remember, we have to conjoin all the implicit guards. What is the other implicit guard? Right? And when this is true, then you can go and yes? So we can build circuits, we can generate all this. Notice that NQ cannot be true unless this is the important invariant, right, which I was pointing out. You can never press the NQ until the corresponding ready signal is available to you. Okay, module is a sequential circuit. In general, read method has no enable input wires. An action method has no output wires. An action value method has both ready enable wires, blah, 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 right? I have already said this. Okay. Register is a primitive module, so this is outside the language. So somebody gives you what the compiler just assumes registers exist, and the methods on a register are you can read it and you can write it. And these are the only things where we don't worry about guards, because it's always true. Right? So register can be read anytime, it can be set anytime. Whether you actually set it or not depends upon the enable signal, and that's our model, registers with enables. But you can do it anytime, because you have the so this is just some syntax. So this is the main picture I wanted to come to. Because what I'm interested in is building circuits with hundreds of millions of gates. And you are not going to do that unless you have very, very, very strong abstractions. And abstraction I have is, it's a sequential machine composed of other sequential machines, cooperating sequential machines. Okay, so I have many, many modules in my design. What is the view I have of a module? It has input methods, right? And we have already turned this into a wiring diagram. So from input methods, I know I have to supply arguments to them sometime. I have to supply them ready signals sometimes. Enable signals sometimes. And what is the output that is coming out of every module? For each method, you have a ready signal coming out. Sometimes you have data coming out. So all the lines that are drawn here have some meaning, right? And hopefully you can all relate to it. These are ready signals corresponding to the data values that are coming out of a module. And this is the enable signal corresponding to the value to be supplied to a method inside it. Register input and output are replaced by method inputs and outputs. So the first time I had shown you when we were starting off ground, we started with registers. But the picture is exactly the same. At the next level, you're going to build combinational logic, connect all these things together, right? And this will have input-output. The point I'm trying to make is, this is also a sequential circuit. So you can design these tiny sequential circuits. You already saw an example. What was the example you saw? GCD, GCD, right? And then we designed a bigger GCD. Composition is extraordinarily important, and composition happens because of atomic rules. It's enabled by the fact that each module has very well-defined interfaces. Okay, rules and method only define combinational logic, and it's getting late in the day, but okay, let me just do one. So suppose you had a module which had an action method here. Okay, so what is the logic connected with this action method? Look, X is declared somewhere else. So whenever you declare X, I already get this. What is the rule of this action method? It's saying, please compile this E expression for me, and you can take A as input because, A came in as input in this, and it produces X as data. And when should this happen? Whenever this method is enabled. So I'm taking the enable part of F interface, and I'm producing. And I could have done it slightly more sophisticated. Suppose you had a conditional assignment. Please do this only if B is true. Okay, so that picture gets more interesting. So this goes out as is, but the enable signal, B has to be true, has to be conjoined with this before enable will be made. Please notice these are all pure combinational things. So for every method, for every rule, you're generating such logic. And then there is systematic way of connecting these wires to other things, and so on. Okay, streaming the GCD module, you had seen all this. This is for your entertainment. So when you go home, draw a circuit for this. If you want, you can draw the circuit for the high performance GCD, right? It'll have even more wires in it. Okay? Finally, so what is the Bluespec compiler? So Bluespec compiler, BSV compiler, generates Verilog 95 RTL as its output. We could have directly generated, registers and gates, but there is a very pragmatic reason for sticking to a known interface like Verilog 95, because all the commercial tools work at that level. So I don't have to worry about that. Once I'm generating this, after that it's all over. I can just use any tool that is available out there for generating circuits below that level. But this is the circuit I'm generating here is exactly the kind of thing I was showing you. I'm just outputting it in Verilog syntax so that I can use Verilog tools. Okay? Simulate this in C. Right? So there is another phase in the compiler, not another phase, another branch in the compiler where you can just simulate it instead of generating Verilog. And our simulators are cycle accurate with whatever you would have gotten here. So for every cycle, you can see all the values of every register, every signal in the system. So the way it's used is you first simulate, right? So when you're doing designs, all the effort is spent here. And only when it has passed all the tests or you have done some formal verification that your design is correct, then you will go to this thing of, you'll do RTL synthesis, and if the design is big, you may want to run it on FPGAs, so you can use Xilinx tools for that. And if you're happy with what's happening there, then you may actually want to go and produce a chip. And then you different set of tools, right, from the same RTL that came out. So at this level, we don't know anything, whether we are going this way or that way. Right? These are all completely compatible things. So for example, when we are doing simple circuits, this is good enough, right? And you could go directly to ASICs or whatever. But when we are doing things like microprocessors, then at some level, this thing runs out of oomph. It takes so long to boot Linux and an out-of-order processor in simulation mode that, you say, oh man, how do I? And it runs, 70 million instructions, says, something is not right, because we are doing. So then, for debugging purposes itself, you start following this path. You map it onto FPGA so that it goes much, much faster, right? And you can start booting Linux in few seconds on these complex designs. And then when it's actually running, then you'll say, okay, now I'm going to start experimenting with ASICs. Let me see how fast a circuit I can build, because that's dependent on many other things. You have to have gate libraries and so on. All right, so final slide, takeaway. I showed you this picture, and I'm selling this picture on the right. I think the most important thing to understand is I'm making no claims about, this is inefficient or efficient. Am I using more logic or less logic here? The main claim I'm making is this is unusable. Literally, this is just unusable, right? The way it exists. On the other hand, if you had defined the interfaces properly and a composition methodology properly, then you have a chance. You can start building things, right? Modular refinement is the second thing, because that is the most important aspect of these designs, that I have a complex design and I want to go and change this module. And I'm not an expert. I don't even understand the rest of the design. And if I cannot work on modules, in isolation, unless I can, once in a while I may go and consult my friend who had designed the other module, but that's usually for performance reasons. Otherwise, we can just, as long as everybody is following the interfaces properly, you can refine your own stuff. So I think I'm going to stop here. Next lecture, parallel execution of rules and BSV semantics. All right.